Okay, so today's topic is knowledge representation, by which I mean how do you store facts in a computer. This is going to get us down the history of artificial intelligence, and it's going to get us down the history of writing down ideas. Really, the ideas we're going to talk about here are the most recent version of ideas that have been talked about for thousands of years. We learned a lot more about them in the 20th century because we started doing things with computers. So just some preliminaries here. What we're ultimately going to build up is relation extractions from text, and your homework will be about this too. And by a relation, I mean subject, verb, object. So there is a type of analytical structure that we're going to talk about again and again today, which I'm going to call a triple. And it is a three-part relation. So one way to think about this is subject, verb, object. So, you know, laptop on table, that kind of thing, right? Or in an investigative journalism conference or context, more likely, you know, some person is a director of some company, right? We're going to see a lot of that sort of thing today. We're going to go into the graph modeling schema used in the Panama Papers, for example. This has a formal mathematical structure that we're gonna talk about today, and an ancient mathematical structure, actually. So that's what we're going to build up to. This ties into the idea of structured journalism, which is a sort of a branch of journalism or a way of thinking about journalism that has taken hold in about the last 10 years. So what do I mean by structured in this sense? What's structured data versus unstructured data?
You have some sense of where, maybe the domain of the data, so you can have structured data and have some kind of tagging or something. Label.
Labels, tagging, okay. So what's an example of unstructured data?
Just corpus of text or something.
Yeah, so corpus of text. So here's my favorite unstructured data source. This is a page from the recently discovered archives of the Guatemalan military police during the military regime there in the 1970s.
The handwriting was so classic.
I know, there's such good handwriting, right? So the police kept incredibly detailed records about what they did, and the hope is that this will provide information about thousands of people who disappeared under that regime. So there's a big project. These have all been scanned by the University of Texas, and there's a big project to analyze them. In fact, a lot of the information in here is structured in its own way. Some of it is lists of people or lists of dates and places and so forth. But as it stands, right, you can't even OCR this. Handwriting recognition is a major unsolved problem, although there's progress. Whereas there's various types of structured data. The most obvious one is tables. We're going to talk a lot about graphs today, and we're going to talk a lot about the relationship between graphs and text. So this is actually an Argentinian court document. And there's a system that the data journalists down in Buenos Aires made a few years ago that annotates these court documents by detecting places in red, and dates in green, and people in blue, and a few other things as well. Okay, so we'll get to more formal definitions later, but this is the basic idea. Structured data in journalism began about 10 years ago. Every block was an early example. It's funny, this seems so obvious now, but this is really the first time anyone had ever seen this. So what every block did is it took public city municipal records, right? So, because governments were beginning to have open data APIs, and just plotted on a map, and you could click it and see whatever it is that that particular document said. So this was every block. It was created by Adrian Holovati off the Night News Challenge, and eventually I think MSN had it. Anyway, it's long gone, but you've now all seen a million things like this, right? But this was a new idea, and actually Adrian at the time wrote a wonderful piece called, there you go, a fundamental way newspaper sites need to change, which I think is linked from your syllabus. And he was at a newspaper at the time. He was at the Washington Post at the time that he wrote this. And he's saying that, just writing stories off the information is not going to work. And he said, well, you're collecting structured information anyway, so you should put it in a database. And he gives all of these examples. He said, all of these different types of stories actually correspond to these standard schema. Schemata? Schemas? I think it's just schemas. Yeah. So he's saying, when we do a wedding announcement, we should basically enter in a database all of this sort of metadata information. Why did he want to do this?
So we can group them by those information later?
Yeah, the idea is we could do something with it later. And unfortunately, the doing something with it later part has been the difficult part, because there haven't been that many cases where this has been important later. And we'll talk about this as well. But you can do this, and we'll look at some famous examples. Another big backer of this idea is Red Schwa at Reuters, who writes a blog on structured journalism and led the Connected China project that we saw last time and we'll look at again. So this was the idea, right? You could collect all this stuff in a structured database, and the information nerd in me loves this idea. Like, yeah, I want to be able to have a database of all of the house fires that the journalist covered. Let's see if we can learn something from that. Again, as we saw last time, the most ambitious use of it has been to make things like this. So this is the result of a huge structured journalism project. Again, notice we have nodes and edges. That's a fundamental representation system. And there's a few other things like this. There are sort of various social networky type articles that people have done. But mostly news organizations have not been collecting structured data in this way. And in fact, it turns out that you can convert from unstructured data to structured data often without too much hassle. And we're going to talk a lot about that today. I think part of the reason that this hasn't taken off is because it's proved possible to avoid it. So I'm going to show you a post by the New York Times, recipes, CRF. Here we go. Extracting structured data from recipes using conditional random fields. So this is an article from the New York Times blog from 3 years ago. And they made this cooking product, and what they did was they took all of 20 20 years of recipes and structured them all. And here's what the structuring looks like. What they're trying to do is they're trying to turn lists of ingredients into a data structure where you have a quantity, a unit, and then the name of the ingredient, and then some sort of modifier on the ingredient. And then you can do fun things like you can search by ingredient, you can use the app to tell you to double the recipe, and it can give you all the new proportions and so forth. And so basically they have to take language, and the first part of this is putting these labels. And they use this thing called a conditional random field to do it. We're not going to go too far into this, but basically what you do is you set up a probabilistic model that goes from a ingredient phrase, so that's the data, right? So very much like our D that we had up there before, to the tag sequence. So this is a statistical model to try to do that. So they can do that, and you end up turning the raw text into structured information. That's going to be it's a standard problem in NLP, and it's going to be a big theme today. So this was the idea, right? We can store all of this data in a structured way, and we can make these fancy sort of stories, or maybe we can sell this data, right? Maybe if we have a database of all house fires, I don't know, maybe an insurance company wants that. This was the sort of idea behind the structured journalism thing. Or maybe we can do inference, right? If we have all of this data, so Reuters had a bunch of reporters working for almost a year to generate the structured data by researching news articles and entering them into a database. Maybe if we're doing that continuously as we're writing the articles, then we can produce content like this without going through the huge effort of converting the text back to structured data. This was the idea. In practice, that's not really what people do. We don't see a lot of projects that involve reporters generating databases. It happens, but it's not super common. Instead, what we ended up with is very sophisticated article metadata. So when you think of an article, you may not think there's very much metadata, right? So well, it's just the author and maybe the date. But there's actually all kinds of other stuff. And this exists today, and I'll show you in a second, that most news sites have actually very rich article data, metadata embedded in the HTML. So this is the structured vision that has come to pass. It has been much less about trying to represent knowledge in a computable form, and much more about trying to make articles visible to search engines and other navigation devices. So there is a site called schema.org, and I will show you schema.org. Schema.org is an open standard ontology, and there's a big word that we're going to hear a bunch of times today. What's an ontology? Yeah, big word. It's got actually a very simple meaning. An ontology is just the set of things that exist. That's it. It's one of the three classical branches of philosophy. So the Greeks said philosophy was ontology, epistemology, and ethics. So what there is, ontology, what we can know, epistemology, what we should do, ethics. And I think they had aesthetics in there as well, which is what is beautiful. So we mostly talk about epistemology in journalism. We're very, very concerned with what we can know. But ontology comes in as well. As soon as you try to make structured data out of text. So here's schema.org. It's a shared vocabulary, and it's a pretty wide set of things, right? So it's sort of built for stuff you might find on the web. So which one of these do you want to look at?
Curious about image. Might not be relevant.
Image?
I'm curious about it, but it might not be relevant. I don't know what else to see.
You know, anything's relevant here. Where do you use image object? So first of all, notice that they show you the hierarchy here, right? It's a tree. Thing, creative work, media object, image object. So that's how they're classifying the world here. Very widely used, right? So this is in HTML and it's saying it's over 1 million domains. And the way this ontology works is each type of object has some properties. So it's got a caption, it's got EXIF data. You all know what EXIF data is? So EXIF data is data in the file. It's metadata for a photograph or a video file. And it tells you like the date it was taken, the exposure, often the focal length, the GPS coordinates, if there's GPS on the camera, that sort of thing. Thumbnail points back to the article. It can tell you the bit rate, width and height, copy protection. I mean, of course, not everything has all of these, but you know, here are all of these things you can have. And each one of these things is itself of a particular type. So if there's other audio, it's associated with an audio object. Let's look at a news article. So how do we find that? Let's say news article. So here's the schema for a news article. Okay, so it's got a dateline. It's got stuff about where it was in print. It's got the actual text. It's got some formatting stuff. It tells you which parts of the page are appropriate for screen readers for accessibility. Yeah, there's all kinds of stuff in here. It's all this accessibility stuff.
So how does this work? Are these standards? Are these recommendations?
I mean, it's a standard. This is the standard, schema.org. You're looking at it.
That's just the standard.
Like who uses this?
A bunch of news sites. So let's look at it.
Who maintains it?
Oh, who maintains it? It is an industry consortium. Let's see if we can get the current list of names. There you go. So that's the founding group, right? So it was the big search engines. And now it's a W3C project.
So the search engines made this standard and news websites conform to it in order to be more easily searchable?
Yep.
Okay.
Yeah,
Okay.
that's pretty much it. So here is a New York Times article from today or yesterday. And here is the source. And I will search for item prop because this is what it looks like in HTML. So item scope, item type, item ID, item prop. This is how this stuff looks like. So item prop is the names that we had on the left, the properties in the schema. So all kinds of stuff, right? So so here we go. Item prop, date published is today. There's like ID numbers here. I don't even know what this is. PubP event, some other system here. There's thumbnail, there's usage terms. So that's like a link to the copyright data. By the way, there is a long and inglorious history of trying to encode copyright licenses in machine readable form. It's never really worked. This was a big dream about 10 years ago, that how DRM would work is each object on the web would have some copyright data attached to it, and then other systems would be able to figure it out. But basically, we're back to a link to a human readable contract. Anyway, this tells us it's in the business section. This tells us it's news and not, I guess, an opinion or an ad. That tells us the URL. There's an ad for the New York Times developer. I love that. All the code that's fit to printf. Cute job, guys.
They really put their jobs listing in that.
Yeah, that's.
That's great.
Anyway, so that's sort of the top level stuff. And then if we keep going, associated media, so there's the thumbnail, here's the captions. This just sort of goes on, right? It has all of this stuff. And then eventually, what we're going to start getting to is the names of the people who are referenced in here. So that stuff gets to, but there's a lot of stuff on this page. Now we're in the scripts. By the time we get past that stuff, eventually we get to the actual article text. Here you go. So here's the actual article body, right? And also around here, we've got metadata on the author. And we should, now it gets maybe a little more sophisticated. We should also have metadata on the people mentioned.
Really?
Yeah. There is metadata here. No, that's still copyright year. Wow, there's some other metadata in here. There's actually several different types, schemas of metadata on this page. Here we go. Okay, so check this out. It says item prop author creator, and it says item type. And this is, by the way, is how you refer to schema.org. You just give the URL. If you want to refer to, what type of object it is, you just give the URL, and then the content of this property is this URL. Right, so it's actually a link to this page which shows you everything by that author. So anyway, that's schema.org, and the purpose of news organizations doing this is to have their stuff displayed directly in various types of search and aggregation systems, right? So you can just get the headline by using that schema data. You can pull the images out. I didn't want to go to that story. There we go. If I get a little more detail, maybe it pulls the date from the metadata, maybe it just does that from its script, but it pulls these images. We've also got things like fact checks. I'm just going to go to Snopes to find something that, there you go, that has been fact checked. So if I search for oh, no, they don't have this one. There's a lot of fact checking built into Google and Facebook now. Normally they would have a little like fact check bar. Interesting. Anyway, but it's to generate this stuff that is the reason they do all of this schema stuff, to make it more searchable. It also, oh yeah, so here's the sort of snippets, right? So, you can put this stuff on an album listing and then Google is able to do this. So that's why the search engines created this stuff. There is further metadata, which is, created by the article indexing team. And The New York Times has actually maintained for over 150 years article level metadata and summaries. It's a remarkable set of data, and so this is from, you can get big corpus for NLP research from the Linguistic Data Consortium, and this is what a little piece of that looks like, right? So for every article, it says, you know, where it, you know, the subject categories, and it lists some particular names, right? So this is a person who's mentioned in that article. And this is actually created by hand by an indexing team today. I think it used to be a dozen and it's about 5 now. I actually have some pictures of this in another presentation. Let me see if I can pull that up. So what it,
It's not internal classification, like it's public, like the New York Times doesn't just maintain it at their end, or?
they maintain it at their end, and you can actually get it in a bunch of big volumes, and it powers a lot of their search. And it's available in some forms and some subsets for research as well. There you go. Here's what it looks like if you get it on paper. Here was an experimental project a couple years ago that they wanted reporters to use that would actually try to use NLP techniques to tag stuff as you wrote and let you try to correct it to the correct tags. But as far as I know, it was never deployed to production. So instead, reporters just write their stories, probably using, you know, Microsoft Word or something and emailing to the editor, because that's, you know, that's where we are in CMS land. And then, oh, I don't have any more slides on this, but this is actually indexed in a semi-automated way. And what I mean by that is they do use computers, but they don't use NLP to do it. Not exactly. What they have is hundreds of thousands of handwritten rules to decide what tags should be assigned to the article. So that's actually a remarkable process as well. A remarkable thing is that they don't actually use machine learning. And they use rule-based tagging. So you can see here what this looks like, right? Here's a story which has a bunch of terms already assigned, and you can see the UI for assigning more terms. So this is done by humans on every single article with machine assistance, and they do not use machine learning to do it. So here's someone you should know. IPTC, I forget what it stands for, International Panel on Telecommunications. They provide the standards for news metadata. And so news codes is a standard coding system for news topics, right? So again, it's an ontology. And it is 4 levels deep. So let's see. Let's see if we can actually find this. Media topics, right? So if you want to say what the article is about, originally based on subject codes. There we go, media topic.
Wait, is this an alternative or a competitor to schema.org, or is it different?
They actually interoperate, so schema.org has a place to say what is the topic, and then you pick the topic from this. There's some overlap, right? You could use one or the other. They have different applications. So for example, the wire services, you know, AP, Reuters, and so forth, use the IPTC codes to label each of those articles, and that is used by the UIs that if you subscribe to those systems, it helps you search for it. So, you know, dance, ballet, modern dance, poetry. It looks like these are forms.
Is this all media topics, or is this just?
This is everything. So in here you're going to see like,
Can fit on one page?
there's an election. Well, it's a big page.
Yeah, but still.
This is not a great viewer. So these codes actually go 4 levels deep, right? So it's a topic tree with topics and subtopics and so on.
Is that something that links to Wikidata too?
Yeah.
This is great.
Yeah. So we're starting to get into the world of linked data,
Yeah.
which is going to be what we're going to spend the second half of this class on. So the New York Times builds this stuff largely by hands. So here we go. And it is hand-built rules of this sort. Okay? So they basically build Boolean searches to index all of these topics, including particular artworks, right? So Nixon in China, which was this opera by John Adams. That's how they differentiate the John Adams who composed that from the John Adams who was one of the founding fathers, is they look for these other contextual words. And you could do this stuff with machine learning, but they don't.
Mm.
Why?
Because it could learn from unreliable sources.
Yeah, because it needs to be accurate, right? So this is what you do if it has to be right. Machine learning is a cheap approximation to this, and not even that cheap because you have to build the training data. And maybe it is machine learning, you know, technically, I don't know, if it suggests new tags and so forth. Anyway, so that's article metadata, and you have to have so you have to control this vocabulary, right? And that's part of their job, is to decide what new tags to add.
How long do you think it took for this system to come into existence?
Well, it's been under development continuously since the index started, right? So I don't know when they built this version of it. I would say probably, guess in the last 10 years.
And they had like buy-in from different newsrooms, and like they must have, or do you think the newsrooms had like different?
No, this is the New York Times. This is not someone else. This is New York Times only. This is their system.
But like IPTC and
Yeah, the standards are,
the standards itself.
you know, gosh, I wonder when the first versions of it were. I don't actually know. I would guess not earlier than about 20 years ago. Yeah, so the IPTC stuff was originally built for newswires to categorize their content to help people search through it. And then search engines consortium produced schema.org because it started to be important to make content searchable. And they interoperate in various ways. So I think schema.org, let's search for schema.org IPTC. What do I want? Site schema.org IPTC news codes. Markup for news. There you go. The genre property can also be combined with much longer lists of IPTC news codes, right? So,
So does that mean the genre property can also be other things, like just straight strings, or does it have to be IPTC codes?
I think it can also be just strings. Let's look. Yeah, text or URL. There you go. All right. So, and here we're starting to see the general pattern that for linked data, which, by the way, was established by Tim Berners-Lee, Sir Tim, I guess, and which is that the subject and the object, in fact, the verb as well, the parts of this triple, each part of them can be a constant literal or it can be a URL. And this is very handy because if you have some page which tells you about a particular object, for example, Ben Castleman, if you want to refer to this person in one of these pieces of metadata, then you just use this URL. Right? Maybe you could say, you know, quote Ben Castleman, and that would be okay too, but giving the URL can give you a lot more information. So the URL becomes also a sort of ID or a unique identifier. So that's sort of where we are with article metadata today. And there is a lot more of it in the New York Times index that is not on that web page. So the New York Times knows all of the people and all of the subjects that are mentioned in that article, and they may or may not expose various amounts of it in the actual HTML. Probably the most obvious application for this stuff is content navigation. Actually Syria is probably a bad example because there's no synonyms, right? So the synonyms are the more interesting problem. So if you search for John Adams, the composer, you're going to find John Adams, the politician. Whereas if you search for John Adams as that object in the ontology, then you can more reliably find everything that is about that person. So that's the first reason we want this. Another thing you can do is go the other direction, right? You can go from structured data to text. So you've probably all heard of the automated story writing that the AP and other organizations do. Yeah, you've all got them from other places. Yeah, we're not really going to talk about that today, but it's very straightforward. There's no magic here. There's no neural nets. There's no machine learning. How this stuff is done is there's a template with different sentences selected based on the value of a data point. So I can actually show you a picture of this. So I like, a lot of people cover this, but I like this particular one because it has screenshots of how this works. So this particular sentence is a conditional, and this is the interface that the reporters use to decide how this works, right? So you can see it defines the conditional here, and there's the yes and no clauses. So very straightforward. Part of me is really annoyed that people are calling this AI. I don't think it's AI. I think this is less sophisticated than Eliza. Anyway, but you can do this if you have the structured data, right? And in fact, Thomson Reuters, mostly as a data company, apparently there's an internal joke, and the way I've heard it said is that, the data makes the money and the news gives them the reputation, which is pretty true. The news division of Thomson Reuters is not normally profitable, but it's a complementary good, right? If they're going to sell this terminal with all this financial data feeds, people really want news on it as well. So they have a news division, and it also gives them prestige to be covering all of this stuff. Okay. So this gets us into the sort of more abstract problems of ontologies. So we're going to sort of get into the whole linked data universe. And linked data started in the late 90s with, there was a lot of excitement about the time, and it was basically an idea of how to put data online using web principles. And the first question they have to ask is, okay, well, what's data? And they decided that a data was a network of triples, just as I've written there. And they made this model called RDF, which is not, none of the data formats are used anymore, but the concepts are still very much in use. And the idea is RDF was a way to model any type of knowledge. And so here it is modeling knowledge about the Beatles. And you can see immediately there's sort of a few consequences of making this choice. So for example, every year, every song duration has to either be represented as a literal or its own object. And you probably want to represent years as their own objects because then you can ask things like, what were all songs written in 1965? One of the things that is a little awkward about this is that you have to use a link to represent even basic properties. So I can't have list the title and the year of the song without having links that are, title and year and so forth. So this is, but in some sense, this is the simplest possible data modeling language. You can't really have a simpler language than this. Now, it is possible to go back and forth between this and tabular data. So actually this has a very clean mapping between subject, verb, object, triples, and a relational database. And there's a bunch of ways to do this, but I just want to try to prove to you that actually this is the same algebra. So the reason relational databases are called relational databases is because the design of SQL is based on relational algebra, which is based on one type of mathematical object called a relation, right? And what it says is that, there's some relation between two objects A and B. And what that actually means in practice is you have a table full of A's, and you have a table full of B's, and then you have another table, which is the relation. And what it has is each row has a key to an A and a B, right? And so what this does is it builds up links between an A object and a B object through this table, okay? That is the relational database. This object, the relation table, you don't always have this explicitly, but part of looking at it this way tells you that you actually generally want this. This is a particular normalized form that is actually very efficient to query if you set things up right. So this is the relational database model. This maps very directly to our graph model, right? So that's it. So concretely, you can think of, you have one table which is all of your, so let's say these are albums, these are songs, and this relation is, what should we call this? Has song, okay? And concretely, if you have 1 million of these, if you were going to do that in a relational database, you can see, okay, well, all of the subjects go in one table, all of the songs go in another table, and all the relations go in the relation table. And then doing a database join is following the links. So if you wanted to ask the question, what are all of the songs on an album? In SQL, what you would say is, do a join where the album is this particular album, and give me all of the places where I have this album and a B, and then give me all of those, that will tell me all of those songs, right? So a database join is equivalent to following the links. If you want to say, what are all the songs on this album in the triple store world, what you are saying is, what are all of the songs that have an arrow coming from A? So there's actually very straightforward mappings between these two types of algebra. However, thinking about it as a graph has certain advantages. One of which is that you can distribute this stuff around the web a lot easier. But before we get to that, I want to talk about ontologies again a little bit. So we've seen a lot of diagrams like this before. Just a clarification, what we were looking at here is an ontology. These are not objects, this is a schema. Okay, so it's the difference between a schema and a table. Here what we're looking at is some actual objects. This describes what types of objects we can have. Now, here's where we get into ancient philosophy. Can we really do this? So how many of you are familiar with the term good old-fashioned AI? Really? Nobody? How many of you are in an AI class right now?
TA for an
Oh yeah. All right, so what's in the course? What are you learning?
Bayesian networks right now.
Okay.
So where does it start? Bayesian networks, machine learning, search problems are the main NLP.
Like Minimax, that stuff? Yeah. Classic stuff. Okay. This is not how AI used to be done. Until the late 90s, AI was done using inference over first order logic. And so I'll try to unpack that a little bit. So here was the idea. The idea is that you could represent the world in logic. And we're going to see some more examples of that. So here's what we mean, right? So we're representing the world in predicate logic. And what a predicate is well, predicates and relations, right? A predicate has one variable and it just says, is it true or false? A relation has multiple variables. I guess predicates have multiple variables as well. Anyway, predicates and relations. And this is the idea. And then you can do things like, for all x where x is a bird, we know that x flies, right? Or, flies x is true, right? You can do this type of thing. And the idea is you could do reasoning by representing knowledge in first order logic, as sentences in first order logic, and then running an inference engine that followed the rules of first order logic. Before you can do that, you have to be able to represent knowledge, which means you need some list of objects and relations. And the idea was that you could only really make smart systems when they had background knowledge. People recognized very early on that a lot of the issue here was context. So think about the John Adams example again, right? Whether it's a composer or a politician depends on whether you're talking about operas or federalism. And to prevent computers from making that sort of mistakes, we wanted to give them common sense. And so various projects were initiated to try to build enormous databases of common sense knowledge. One of the most famous was Psych, which was short for encyclopedia. And before you can encode knowledge, you need a list of things that there are, you need an ontology. And this is a piece of the ontology from Psych. Right? So it starts with thing at the root, and then we have partially intangible things, and then we have intangible individual, which I guess is just a one-off, a situation temporal. Oh, finally we have an event. Right? So we get these extremely abstract categories. And you can see that, there's lots and lots of different ways that all of this stuff could be organized. I had another ontology in here. Yeah, here we go, right? So here's a little more concrete one. But why is restaurant classified as traditional, international, or exotic, right? Like, is that the right way to break restaurants down? So Yelp has this problem. Now, The practice of representing knowledge as first-order logic over some vocabulary and reasoning about that logic using the standard rules of inference. And so you can kind of see how this works, right? So first-order logic has rules. You start with some set of rules. You have production rules that tell you how to go from something as true to something else. You turn the crank, you learn a new fact. So, is everybody familiar with this idea? Let me give you the simplest possible example of this. And this idea really is ancient. It's so ancient that the rule I'm going to give you has a Latin name, right? So this is modus ponens, which means the bridge method, right? You've all seen this?
Yeah.
All right, so, but I want to look at it slightly differently. If I have a rule which says A implies B, and I have A, then I also have B. Okay, so I'm armed with this rule, and in fact, you don't need too many more of these. You only need like 3 or 4 of these. And you start with a huge amount of information stored as these types of propositions. You can turn the crank and you can produce many, many more true statements. And then you get to inference algorithms that try to prove a statement, so that then it becomes a query. Is there a song? Did the Beatles publish any songs after 1970? So then you're trying to find, does there exist an X such that, X is a song and the author of the song is the Beatles and the year of the song is after 1970, right? So you can sort of see how this works. And they thought that this was how they would get computers to do common sense. It didn't work. Why? The reason it's an important question is, first of all, it's of philosophical interest because it is deeply related to the problem of what knowledge means. And people have been thinking about this for thousands of years. And it's a hobby of mine. I collect quotes and people being like, yeah, we can mechanize knowledge. This will totally work. It not only hasn't worked so far, but I claim that it can't work. So why, right? Like what we're bumping up, so that's the philosophical question. The practical question is, what can we expect to be the limitations of representing knowledge in this kind of graphy way? Which we still do today, right? We do it all the time in journalism.
Practically, like a particular object could be in different places in different contexts. Like a hospital, or I don't know, it could be in 2 categories, or like if you wanted to get historical data, it could be interpreted in different manners.
Yeah, so you're on the right track here. There's
In could be accommodation, but it could also
Yeah,
be like
that's
a bar or something.
I wanted to say hospital could be an emergency service and attraction. I was like, no, it can't. So that's not an example.
Yeah, right. So one way to think about this is the flightless bird problem. It's really hard to make an ontology in general knowledge because there's always exceptions. If it's a bird, then it flies, except if it's a flightless bird. So then you have to list every exception.
Oh.
And should bird even be a category, right? Even surprisingly simple predicates break down into special cases, right? Even something like above or below, right? The apple is on the table. Okay, well, what if the apple has fallen partway between 2 desks? Is it above or below the table at that point, right? So reality has a way of breaking ontologies. There's just seems to be too much ambiguity in the world to really nail down rules in these ways, and also it turns out to just be extremely difficult to write a set of rules that will work. And there's some various famous examples in the 80s that people really made the attempt, to do this for domains like fluid. You know, like they had rules like, you know, if it's not full and fluid is flowing into it, then the amount of fluid is going to increase. And they had hundreds and hundreds of these, and it just didn't work in practice. You know, you always had these weird exceptions. It was very fragile. And this is kind of why statistical methods took over. And yet, a lot of these ideas persist today. So here's the idea that sort of, and all versions of structured journalism just sort of boil down to this, right? They can be transformed to this in some way. Is we have these types of relations, and then if we had that, we could run interesting queries and inference on it. And in fact, this is a real query language. This is a query language called Sparkle, which was a query language designed for linked data. And so you can see how it's sort of very first order logic E. You know, find me an X such that there's also a Y such that this relation between these two holds. Or in this case, you get to use these inference rules to infer that Bob's your uncle. But you can kind of see how this would be useful, especially if you're doing things like, you know, investigating business networks or money laundering. Yeah.
Going back to your philosophical question, I guess then modeling things like family structure, which is pretty much concrete in society, is easier than modeling other things like fluids or like planets, because we're always like, we don't know what science is. We're always debating, whereas we know that certain things that are hypothetical concepts in society are like, I don't know.
Yeah, so the way that I like to think about this, and this is a way of thinking about what types of problems this will work for. The type of problem it's most likely to work for is those problems where there is societal institutions whose job it is to enforce the concrete binary nature of a relationship. So for example, property ownership, okay? In certain places in the world, the system of property ownership is less developed, the legal system is less developed, the maps and titles are historic, and you know, somebody owns that house on the edge of the village because their family has lived there for generations. Right? There's no documents to that effect. When you start to want to formalize these things, well, I mean, in practice, how society formalizes the notion of property ownership is they take a book and they write a line down the middle of the page and they write name on one line above one column and they write property above the other. And now you have a list, a relation, in fact, of which person owns which property. Right? It's exactly that A-B relation we were just looking at. And then you build systems on top of that. You hire officials whose job it is to maintain the book, and they get to decide when entries are added and removed or changed. And then you build a court system whose job it is to arbitrate disputes about this book, and on and on and on. And the point I'm trying to making is that the concreteness of the property ownership relation is maintained and enforced by very sophisticated societal infrastructure. And that makes it dependable. And that makes it particularly dependable in the journalistic sense, because you end up writing sentences, factual claims of the form, according to public records, X is the board of directors of Y company. Like, these are all fictions, right? What's a company? What's a board of directors? But they are fictions maintained by very sophisticated apparatus. And that actually makes them very easy to use this type of reasoning about. Marriage is another example. You're married or you're not. Now, of course, marriage is many, many things. You know, it's whether the people live together, it's their relationship to each other, it's, you know, all kinds of things. But it is also a legal contract. which is enforced by the state. And the state does not allow people to be kind of married, right? The state enforces the binary nature of that relationship. So interestingly, there is a philosopher who wrote a book about this point. Made the point that although we tend to think of the truest kind of truth as physical theory, physical law, you know, it is objectively true that gravity exists. I mean, sure, I'll buy that. The types of truths that we are actually most sure of are social truths, right? Albany is the capital of New York. That is both entirely social and completely beyond dispute. Why is it the capital? Because we said it was. That's it. Okay? So you can put that type of knowledge into a graph database, and the ontology and relationships are extremely clear. Anyway, this is a bit of a detour, but I find this particular detour fascinating because it runs extremely deep. This is at the heart of AI, it's at the heart of epistemology, it's at the heart of the social construction of knowledge, and if you can figure out how to use it effectively, you can do a lot of really cool stuff. So, I think we'll take a break, and then we will do linked data after the jump. So we've been focusing in on the problem of ontology and knowledge representation. One of the issues is that although a number of newsrooms have their own schemas for encoding this type of information, and some of them are producing this type of structured stuff, they're all different. And this is not just a problem in news, this is a problem with everything. It's that because ontologies end up being so subject specific, everybody makes their own. So, 25 years ago now, there was a solution proposed to this, which is linked open data. How many of you have heard of this? So linked open data was, I'm actually not sure whose idea it was originally, but it was championed by Tim Berners-Lee, and there's a linked open data TED Talk linked from the syllabus. And the idea is pretty much what we've seen today, right? So it's triples. Data is represented by triples, but each element of that triple is either URL or literal, and it's the URL that makes this linked. So check this out. Here is a triple that connects an object in DBpedia, which we'll talk about in a second, using a relation defined by W3C to a category defined on schema.org. So we've now got a relation that crosses 3 different ontologies. And the idea is that people can put information online by publishing objects and predicates just by making a page for them. And it doesn't even matter what's on that page, right? So if I go to this page, it's a human readable description of Columbia University, and then referencing them like this. So here's what this actually looks like if I go to that DBpedia page for Columbia University. And what DBpedia is, it is a structured version of the sidebars in Wikipedia. So if I go to Wikipedia and I look up, let's see, the Jordan River. Okay, so check this out. This is structured data. It is a template. How you do structured data in Wikipedia is you use a template. This one is called GeoBox, which apparently is being considered for deletion. But, you know, it has all of this information, like where it is and the tributaries and the length and an image and a caption on the image, right? So if you take all of this stuff that's already in structured form in Wikipedia you get dbpedia. And now I can refer to this thing by a dbpedia URL. So if I go dbpedia Jordan River, yeah, here it is, right? So if I want to talk about the Jordan River, I can use this URL. When I actually go to that URL, I get all this other information, including all of the properties of it. And what these are just other relations, right? It's saying here's another relation and here are the things that it connects to, that it knows about, right? Not everything on the web, because that's like asking the page who links, asking the question who links to me. It's a difficult question to answer.
Google used to do that, right? You know,
Do what?
the link back thing. Ask.
Oh yeah, well, I mean, Google knows, they just don't let you query it easily. Yeah.
Is there a reason for that?
I mean, I'm sure there's a reason. I'm not sure what it is. I don't know if Google Advanced Search lets you search for it anymore. Table that. Now to search it, they've got this little thing called, clear this, Sparkle endpoint. Sparkle is a query language for graphs. And this will only query things within dbpedia. I'm going to come back to this in a second because I don't want to go off on a tangent on graph query languages right now. But this is the idea. Now, the thing that makes this linked is that it's possible to refer between different data sets. So this is the linked open data cloud today. And you can actually go to, where is this? There we go, lod-cloud.net. And you get this diagram. This is an SVG, so it's this super high resolution thing. And you can see at the center of the cloud, there's dbpedia right there. A more recent project out of Wikimedia, because this is so popular, is Wikidata. So Wikidata is similar to, in concept, to dbpedia, but it's not just scraping stuff that's in Wikipedia. It's actually like a data-centric Wikipedia. And both of these projects, dbpedia is much older, so it's still very much used, are at the center of all this other stuff. It's a little hard to see in the middle here, but if you, whoa, there's another dbpedia. Is it the same one? dbpedia abstract corpus. No, it's not the same. But if you zoom way into this stuff, and by the way, the colors are the usage, right? So there's a lot of, oh, they know life sciences, right? There's a lot of medical stuff, which is this blue color. So like all of the proteins and diseases and drugs are in big databases, and they're all linked to each other, right? So like this is a database of lipids. And when, and this is a database of organic compounds and so forth. And then there's geographic information, so geography. So I bet you there is a blue thing. Yeah, geonames. Are you all familiar with the geonames database? Yahoo originally built this. It's an open database of geography. It's hierarchical, so regions can contain other regions. And basically, whenever one of these other databases needs to refer to a place, it refers to geonames. Okay, so other things you can do. You can specify the type and look at dbpedia here. Look at all this information. It says what type of thing it is in more than a dozen different ontologies. So OWL is the object web language. Each of these is a URL. And also a human readable page describing what it is. There's the Wikidata object that represents a country. And this is what a similar page for Wikidata looks like. This is what a single entry in Wikidata looks like. So let's search for an item. Suggestions?
Any item?
Yeah.
Mortgage?
Mortgage loan. Loan secured using real estate. So it's an instance of credit and an interest of subclass of loan. Oh, different from, interesting. And then it gives references into other databases. Freebase was an early sort of precursor to Wikidata, a sort of everybody contribute all of these structured data facts. Freebase was bought by Google and became the basis of the Google Knowledge Graph. The Google Knowledge Graph is the thing that populates these boxes on the side. So look at this. This is structured data that Google has. And one of the interesting things about this is same as. Oh yeah, here they do it with an identifier list, right? So what we have here is also a list of all of the other things that this is in different systems. And these crosslinks are the things that tie the database together, or tie the linked data cloud together. Right, so objects, so I can make a relation that refers from one database to another. Also, there's information in each database that says that two nodes map to the same thing. So the way you represent that classically is the OWL same as relation. So OWL is that classic language. Do I have any same as relations here? No. I think later on this page there was. So this gives a way to tie all of this structured data together. Now, you can query this. There's a query service. So, for example, we can find all cats. And this is a language called Sparkle, which the abbreviation escapes me for the moment, but it's a structured query language. And if I run it, I get everything which is a cat. Which one do you want to look?
Marble? The first one?
Yes.
Marble.
It's a cat.
Member of a Japanese musical group. There we go.
Okay, that is a very interesting entity.
There's
So it's both a
a
cat
cat
and a
part
musician.
of the music.
It's an instance of cat.
It's a female cat.
I don't think they have it as a musician here.
It says member. Oh, it's just a.
That's the text, but I don't see the statements about it. It's a member of Musashi's.
It's just
There you
the
go.
cat.
Oh, it's all cats. Humans without children. Okay, so here's a query. There is a bit of a query builder somewhere that I can't find right now. Here's the answer, and then I can get this stuff in a variety of ways. So in particular, that query is now at an endpoint, and when I hit that endpoint, what I actually get is a text file, or I think actually a CSV with that data. And this is all alive. So what I've done in you can get it in any of these languages here. What I've done in another case is queried for all battles in the 20th century and taken that URL that it produced, which is this horrifying URL here, and thrown it into Workbench, so it just loads this table with the start time and a little bit of cleanup and filtering and so forth. And what I can get is a list of all of the battles recorded in Wikidata. And so, of course, I get peaks for World War I and World War II. So there's a lot of stuff in here, and you can imagine a lot of crazy uses of this. And there are query tools which allow you to query across this linked data cloud. Oh, there's the Earth. Okay. So that is linked data. Interestingly, some news organization APIs return linked data. So for example, here is the New York Times API return for a particular article. So you can get the first paragraph of articles from the New York Times API. And it has in it links to, I don't know if they still use DVP or if they're on Wikidata or what, but it has URLs which link into the linked open data cloud so that you can define what that article actually talks about. So this is all very nice. It's nice to bridge news articles into sort of the web of structured data, which is what linked open data is. But we've started to see a different use of these principles in journalism, which is for investigation of large data sets. So we saw this a little bit last time in our network analysis stuff. I'm going to formalize it a little bit today. First, I want to build up a more powerful model. So the triple store model is capable of representing everything, but maybe not conveniently. It's very convenient to be able to just put literal values on a node or relation. So instead of having to link to a year that is 1970, I can just put on it as a property year 1970. Now I hope you can see how you can convert between the property graph and just triples. It's a very simple transformation, but it can be very convenient to actually do it this way and to think about objects as properties which have relations between them. So the property graph tends to be the graph relationship that is used in practice by production graph database systems. One of those is Neo4j. Neo4j is an open source graph database. It stores all of its data as graphs, and you can query only using a graph query language. This is not data but a schema, and this was the schema used to encode the structured data in the Panama Papers. Now, the Panama Papers was actually mostly unstructured data. It was mostly emails and PDFs, but it also included database dumps. That is to say, a whole pile of tables. As we've already seen, you can translate tables into graphs in a pretty straightforward way. And actually even more straightforward for property graphs, because each row in the database just becomes the property, it just becomes one node, and the values of the columns for that row become properties. Right? So there's a very straightforward mapping between tables and property graphs. And this is the schema that they used for the Panama Papers. There's a nice blog post about this, so which I've just put in the Slack. Here we go. This is there's a lot of discussion of how graphs databases were used in the Panama Papers, but this one talks about the schemas in good detail. So there's the link. As you can see, the structured data is it's less than the unstructured data when you put the PDFs and emails together. There was a lot of OCR. It turns out they never actually did named entity recognition on the documents. So the graph data for the Panama Papers was purely the structured data. But this is what you want to do, is you want to try to pull out the entities and relations. And when you're doing tax evasion stuff, what you're really looking at is a concept called beneficial ownership, which is who does the money go to ultimately? And if the money is assigned to company B and we have this type of structure, then ultimately blah, blah, blah is getting the benefit, right? And so if company A is a shell company and is registered in a jurisdiction like Panama where it's difficult to get the directors of that company, then that is a way of hiding the fact that Bob benefits from company B's income. So what we're starting to see here is pieces of the Cypher query language, which is the proprietary query language of Neo4j. And you can start, there's the data model we looked at. You can start to write queries for this stuff. So, whoa. That actually just loads the data. Here we go. So here's a query, right? So you can find a person who contains a particular name. You get a query back. And then you can click on that node and expand it to see all of the links out of that node. So you can use it in a very basic way, just exploring the database. Or you can start to look for more complicated things, right? So here's where we have unbound variables. We're saying find someone who's an officer by this name, and then show me all of their relationships to companies, right? So we're saying R and C are free variables. We're looking for any companies where this officer we found is related to them. And so we get this graph, right? So here are the people where the name matches, and then we can see that they're shareholders of various companies. Now you may have noticed that the same name appears multiple times. We saw this last class, this is the problem we had before. That's because we load the same information from multiple databases. And so we have to have some sort of record linkage solution. So normally what we do is we add an edge when we detect that things might be the same person. But that's the general idea. And we can now, I mean, in theory, you can set up these complicated graph queries that are like, oh, hey, we've discovered that in order to hide all of this money from this crazy real estate transaction in Uzbekistan, they set up 5 different companies, in the week before 13 April when this transaction was executed. We want to find everybody who the money might have been going to. So let's find any company set up in a tax haven in 13 April that has any connection to this one person who we know was already involved. So you can imagine a complicated graph query, right? So find a company where there is any path to this person that has the property of being incorporated before 13 April. So has a path to is a graph query that you can execute. And there's no magic here. Anything you can do with a graph query, you can do in SQL. So finding the path between 2 nodes, you can do with recursive joins in SQL, which, is not frequently used, but it's in the language. So you don't get any more power than SQL, but it's a different way of thinking about these problems. And it sort of lends itself to these nice visualizations. So this is sort of where the future of investigative journalism is going, is fusing large sets of data from multiple sources in graph databases. This seems to be, it's not that you can't do this with SQL, and sometimes maybe you should. It's just that the conceptual model, and in certain cases the algorithms, are optimized for these types of path tracing, pattern matching problems. Okay. That still leaves the problem of extracting relations, these types of triples from documents. If it comes in a structured form or we're using linked data, fine. But if it just comes as documents, which again, most of the pen and paper papers did, how do we deal with that? This is an active research area of NLP, fortunately. So again, we're looking at our Argentinian court document. I actually have no idea what this one is about. I grabbed it from their website. And you can see here that we've done entity recognition. That's the first step, is just figuring out, who's involved. And actually from that you can build a pretty good graph. The only graph that you can build it has only one relation, right? 2 entities appear in the same document. That's it. But that is often enough, right? So for example, if you have an incorporation document, you may have the relationship, the document may actually say that person A is a shareholder of person B, you don't have that shareholder relationship, but just by appearing in the same document, you have some relationship. So that can help the reporter find these connections. So that is sort of the baseline of how you pull entities. You have one relationship, appears in a document with. It's more powerful than you might think. So the first step of that is named entity relationship. There is the interesting question of what an entity is. One of those problems is called resolving anaphora. Anaphora is where one word refers back to another. So for example, you might want your NER algorithm to pull out this he here and know that it's the same person. Or you might not care. You might not care how many references there are. Going one level past that, you should be able to pull out relationships between entities by looking at the verbs. So here's a very simple example, right? Except it's not actually that simple, right? Workers, that's easy. Pumped, that's easy. The basement of CHP hardware. Well, that could be a difficult entity to represent, you know? What is that? More generally, there are this problem is called information extraction. There are systems, including open source systems, to do this. This is the Stanford OpenIE system applied to a lyric from Journey. And the way it works is it breaks sentences into individual clauses. So here we actually have 2 clauses. And then it basically repeatedly strips them down until it gets a triple, right? So born in a small town, she took the midnight train going anywhere, turns into 2 triples. She took midnight train and she born in town. So we strip off the adjectives, we split the clauses. We can kind of pull this stuff out of text. And so you can imagine feeding all of these documents into an information extraction system and pulling this stuff out. So far, to my knowledge, nobody has done this. In fact, even on the Panama Papers, they never ran name entity extraction on it. That blog is wrong. I've talked to the developers. It's the obvious thing to do, but they never did it. In part because it's an extremely computationally expensive thing to do on millions of documents. And also in part because what you would get would be a catastrophic amount of noise.
I found that out last night.
Oh yeah? What were you
I
doing?
wrote last night to do this very thing. I ran it on the AP document set that you gave us earlier in the semester. And I used Spacey for name entity recognition, and it's just really noisy. So I'm thinking of training a model
Mm-hmm.
and making that my project for this month.
Mm-hmm. Okay. The other problem you get trying to do relation extraction is that the ontologies just blow up when you actually try this, right? Because, how do you parse this text? This is a thing about Hurricane Sandy, obviously. Was a mixture of, is that a relation that should be in your ontology? What do we do with group of young men in pajama pants and shorts? Right, is that an object that should be in your ontology? So if you apply this to sort of general English text, you're going to have problems. And these types of problems are why it hasn't really been done yet, but it's coming. We'll figure out ways to solve these problems, I think. And I think what we're going to do is we're just going to have better filters either on what we extract or on how we display the extracted data. One of the places this can ultimately build up to is general question answering. So that is to say, I feed all of these documents into the computer, and then I say, computer, who is moving the most money through Panama? Right? Or show me the complete trail of companies connected to this transaction. And the most impressive production system is actually quite old. It was IBM Watson, and I'm actually going to show you a short video on how they built that system. Arguably, it's out of date. There's no deep learning. It's built with technology from 10 years ago, basically. But it discusses many of the issues that would be required in building a general questioning answering system for investigative journalism. And as we'll see, it's kind of a nice counterexample to this theory that you can put everything in a graph, because it uses graphs, but not in the way that we've been talking about them.
Let's take a look at our single Jeopardy categories. Patricia, where do we start?
Famous Americans, 200.
This New Yorker who fought at the Battle of Gettysburg was once considered the inventor of baseball. Watson.
Who is Abner Doubleday?
Good for 200. Choose again, Watson.
So the Jeopardy challenge provides this compelling and notable way to drive and measure the technology of automatic open domain question answering. And it does that along 5 key dimensions. First, a broad and open domain. Jeopardy asks about all kinds of things. It's really remarkable the breadth that the questions cover. But what about the language itself, right? These questions are richly formulated questions, a wide variety of grammatical structures, interesting expressions used to refer to a huge variety of things and properties and various kinds of things.
BID means you take an RX this many times a day.
So broad open domain, complex language. Also, you have to have very high precision to be good at this game, and we're going to talk about how high in a bit. You have to really know your stuff. But one of the most important aspects of Jeopardy, and one of the things that really interested us, is the need for an accurate confidence. Because what happens in Jeopardy is if you get one of these questions wrong, if you buzz in and you think you know it, and you actually get that question wrong, you lose the dollar value associated with that question.
100 R's. Mandy.
What is an acre?
No. So what you have to do as a player, and what Watson has to do as a computer, is calculate a confidence. 70% sure, 50% sure I'm right. And then manage that risk and make a decision of whether or not to buzz in. And finally, you have to do this quickly. To compete at Jeopardy, you have to have high speed. When Watson plays Jeopardy, it's entirely self-contained. It's not connected to anything. It's not connected to the internet. It's not using web search. All its algorithms and all its data are inside what looks like the equivalent of about 8 refrigerators. So there are actually 3,000 cores running simultaneously. There are terabytes and terabytes of memory. But ultimately, what you see is what you get. And this was important when you think about challenging humans at this task, because what we want to do to engage the broader audience is for them to kind of start thinking about, gee, what can computers do? And what are their strengths and what are their weaknesses? And how does that compare to what humans could do at any given task? We can start looking at, well, here's the human, takes up this much space, it's got a brain that fits in a shoebox, right, powered by a tuna fish sandwich and a glass of water. But when we look at Watson, we say, wow, 8 refrigerators, tons of air conditioning, megawatts of electricity. Right, so what does it really take for a computer to start to even scratch the surface in dealing with this kind of natural language processing, question answering task? So on that note, let's talk a little bit about what computers find easy and what computers find hard. How about this question? The natural log of 12,546,798 times pi squared divided by 34,567.46. Anybody? Greater than or less than 1? You got a 50-50 shot. Greater than 1. Well, it turns out the answer is 0.00885, less than 1, and a computer does this very, very rapidly, really instantly. So computers are really good at doing math, doing arithmetic, processing large equations and formulas, doing scientific computation. Remarkably good at that. IBM has created very powerful computers to help in this domain. So what kinds of things do computers find hard? Well, natural language in particular, right? Because it's implicit, it's highly contextual, it's ambiguous, and it's often imprecise. So let's think for a moment about a question. Where was X born? And you could fill X in with whatever you like, some person's name. So let's say it's Albert Einstein. And let's also assume that you program the computer to know that when you ask that kind of question, you associate it with a table or a database. And you put the name into the person column, and you went over to the birthplace column, and you pulled out the answer. Well, that would be very simple, right? I have all the information I need. We call this kind of information structured. But imagine I had what we call unstructured information, where the meaning is not explicitly defined for the computer. So imagine it just had to read a bunch of stuff, and it came across this sentence. One day, from among his city views of Ulm, Otto chose a watercolor to send to Albert Einstein as remembrance of Einstein's birthplace. First of all, why would it pay any attention to the sentence? Because I couldn't tell it ahead of time that to answer this question, it had to read that sentence. In fact, it has to read a bunch of stuff. And it has to figure out that this sentence might answer that question. But why would it know that? It doesn't talk about anybody being born here. It talks about a birthplace. But what does a birthplace have to do with being born? The computer would have to know that. Why would it know that? Again, if it couldn't anticipate all the different kinds of things you might ask it. It has to know who the people are, who the places are, and how they're related to one another. So maybe if it could figure all that out and parse that sentence, it can come up with an answer for Albert Einstein with some degree of certainty. How about this question? This fish was thought to be extinct millions of years ago until one was found off South Africa in 1938. Anybody? Coelacanth, very good. That's correct. And you can imagine that, if I just looked at this one question and thought, gee, I'm going to solve Jeopardy by building a big database of every question that can be asked about fish, every possible fish, and all the properties of fish. What would happen is I would cover like 0.001% of the data. There's no way I would be able to cover the huge breadth that's represented by the Jeopardy space. So we do not anticipate all questions and build specialized databases. Rather, our focus is to use as-is information. Encyclopedias, dictionaries, plays, books, using information as it exists and making the computer smarter in analyzing that content to compute answers and confidences. One of the ways we try to mine information, mine knowledge out of existing resources is by analyzing them. We have computer programs, algorithms that will read text as volumes of information. It won't understand it in the depth that humans might understand it, but it starts to look at it structurally, syntactically, and semantically, meaning it tries to tear it apart and understand where the subject is, where the object is, where the verb is, where the preposition is, how they all relate to one another, what part of a sentence modifies another part, and so forth. So it takes that text and produces these subject-verb-object graphs, right, with all that information in there. And then what we do is, with that information, computer algorithms start to interrelate, correlate, and compute statistics and confidences associated with that information it's extracted from that text. So it can learn things like inventors patent inventions, or officials submit resignations, or might learn people earn degrees at school. It might learn that vessels sink, that people sink 8 balls, but only in the context of pool, right, the game of pool. So we can learn all of that, right? We can aggregate that information and use that. Here we have an example. In cell division, mitosis splits the nucleus, and cytokinesis splits this liquid cushioning the nucleus. So we have to start looking at what the question's about, doing many, many searches, and generating different possibilities, like organelle, or vacuole, or cytoplasm, plasma, mitochondria, blood. These are all what we call candidate answers. Put back in the context of the question, they become hypotheses. And now what the computer's challenge to do is look at, given all the information I read, can I support one of these hypotheses as being more true than the other? So it generates what we think of as intermediate hypotheses. Is cytoplasm a liquid? Is organelle a liquid? Is vacuole a liquid? Is plasma a liquid? And it finds this sentence, for example. Cytoplasm is a fluid surrounding the nucleus. It says, well, gee, is fluid a type of liquid? And of course, there are many algorithms inside Watson. Some of them look at different kinds of resources. A particular resource it looks at is known as WordNet, which is a rich thesaurus and taxonomy, a classification tree of different concepts. And it uses it to determine whether or not fluid can be considered a liquid. And of course, because it's a precise resource and looks at the actual physical knowledge, right? A liquid is a type of fluid. A fluid is not a type of liquid. So it comes back and says, I'm sorry.
So in this case, the ontology failed it.
But if we looked at those learned resources, right, all that information the computer algorithms extracted from the text, what Watson learns is the way people use language, that in fact they sometimes consider fluid a liquid. And through training, Watson learns that this information that it mined from those large volumes of text is useful and predictive in the domain of Jeopardy. In May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. Anybody? Columbus, good guess. No, Columbus thought he was arriving in India, no. Actually, the answer is Vasco da Gama. But one of the things I want to talk about here is the notion of evidence. Some evidence is more trustworthy or more predictive than other kinds of evidence. So if we took this question and broke it down into a bunch of different keywords, and we went out and did a search, we, for example, would consider this passage a really good hit. In May, Gary arrived in India after he celebrated his anniversary in Portugal. It's a great passage. It has all the keywords in common. It's got arrived, it's got celebrated, it's got May, anniversary, Portugal, India. And what it suggests is that Gary is the answer, that Gary is the explorer in question. And who's to say Gary's not an explorer? You can imagine the next sentence here reading, and Gary returned home to explore his attic looking for a photo album. That sentence is legitimate evidence that Gary can be classified or considered an explorer. It has Gary as the subject of the verb to explore. But is it good enough evidence to support Gary as the right answer? Could there be better evidence? Here we have the same question, but we have a different passage. On the 27th of May, 1498, Vasco da Gama landed in Cabot Beach. Here we have only one keyword in common, May. Why would I even look at this? There has to be tens of millions, if not hundreds of millions of documents that contain the word May in it, right? It's used all the time, it's an ambiguous term. So even if I got to the point that I'm willing to consider this passage as possibly containing the answer, I now have to figure out how I'm going to match it. How do I relate what's discussed here with what's mentioned in the question? I need a whole ensemble of different algorithms to try to do this matching. So temporal reasoning algorithms can look at 400th anniversary in 1898 and relate it to 1498. Statistical paraphrasing algorithms can learn that, you know what, landed in and arrived in appear in similar contexts and therefore might be similar in meaning. A geographical database and some geospatial reasoning can tell me, well, gee, if I'm in Cabot Beach, I'm actually in India. If I've landed in Cabot Beach, perhaps I've arrived in India. This matching allows the system to hypothesize that Vasco da Gama is the answer and the explorer in question. And it should, in all its resources, get more evidence that Vasco da Gama is classified an explorer, at least more so than Gary is. So how good are humans at this task? What is a computer going to have to do? How good is it going to have to be to play human champion? So we looked at thousands of historical Jeopardy games, and what we did was we plotted the performance of the winner of those games. So every dot here represents at least one Jeopardy games, and what we looked at along the x-axis is the number of questions that the winning player got to answer. You see that the winning player answers nearly 50% of the questions in a game. And you'll also see that on the questions that they actually get to answer, they do somewhere between 85 and 95% precision. That's remarkably good. We have been working on a state-of-the-art question answering system in very good company with universities and partners. And this is back in early 2007 that we did this. And what we discovered was that on the 5% it was most confident in, it only got 47% right. As it had to answer more and more questions, its confidence dropped and its precision dropped. So by the time it got out to answering 70 or 80% of the questions, it was down at only 15% precision, leaving a huge gap to get to the winner's club. And this is what, as a team of researchers, we had to face. What we came up with, which is this is the core technology underlying Watson, we call it Deep QA. It's a massively parallel probabilistic evidence-based architecture. So what does that mean? Massive in the sense that it's looking at many, many possibilities, starting from the original question, generating all those possible searches, all those possible answers, all those possible pieces of evidence. And then as this fans out, you have hundreds of thousands of evidence answer pairs, and now you have this big ensemble of algorithms that analyze that evidence, compute confidence scores, and ultimately have to rank all those answers and those confidence scores. And what we do here is we apply what we call learned models. We use machine learning. The system learns how to do self-assessment. It learns how to weigh those algorithms with respect to each other, and we start to refine those algorithms. But as we progressed over the years, of course...
So that's the key insight. Many different methods, and you learn when to use each one.
So here's a few examples. The Queen's English Give a Brit a tinkle when you get into town and you've done this. Watson, urinate. I didn't think that was too bad of an answer, but the correct one is, of course, call on the telephone. Fatherly nicknames. This Frenchman was the father of bacteriology. Watson, how tasty was my little Frenchman? Right answer, of course, Louis Pasteur. Confidence is king, so it's only going to ring in if you compute that confidence and that answer fast enough. It uses that confidence to make betting decisions and to manage risk. And one of the things you'll get to see is what we call the answer panel, which are Watson's top 5 answers. And here we have an example. In August 1812, a U.S. frigate got this nickname when British cannonballs were seen to bounce off its thick oak hull. And of course, what happens there is Watson has a good amount of confidence. This little indicator here is its threshold bar. It says, if my confidence bar is over that threshold, I want to buzz in. So it has enough confidence to buzz in. But it's wrong, actually. It's because the question's asking for the nickname, which is Old Ironsides, actually had that in second place and below confidence. So Watson will try to buzz in here, and if it wasn't a buzz, it would have been wrong. Watson can also learn within a category, so it can develop and adjust its confidences based on what's happening within a particular Jeopardy category. As more clues get revealed, Watson starts to see what kind of thing the answer is, so it dynamically adjusts its confidence and starts to say, wait a second, maybe I was wrong about what kind of thing this question's asking. So Watson learns dynamically during a game, as well as when it's analyzing and trying to read and understand and train prior to a game. Now, one of the things that's interesting to note is when we take the deep QA computation and we run it for Jeopardy, it took about, on a 2.6 gigahertz core CPU, so for example, a typical desktop computer, it took 2 hours to answer a single Jeopardy question. That would make for a very, very boring game, of course. So what we had to do is to take that computation and scale it out over thousands of cores, thousands of CPUs, if you will. And we use a high-performance computing platform, IBM computing platform, that actually allows us to run many, many, many parts of the algorithms all at once on 3,000 cores simultaneously. And that system is able to answer questions between 2 and 6 seconds. So do we answer all the questions in time? No, but the vast majority of them we can answer in competitive time, meaning we can compete with grand champions in terms of precision, in terms of confidence, and in terms of speed. So our original system gave this particular confidence curve, and it wasn't until about mid-2007 that we ended up developing that deep QA architecture and starting to populate it with lots of different algorithms. And what happened was we started to see very early and important results. By early 2008, we actually made a huge leap by exploiting the deep QA architecture. But we saw incremental progress over about a 4-year period. You see that last line that we measured in April 2010. And what it's doing is it's slicing right through the winner's cloud. It's showing that the computer can be competitive against champion players, that on a large volume of the questions, it's doing between 80 and 90% precision. This is really, really remarkable performance and a dramatic leap from where we started. In 43 games against champion players, Watson's winning over 65%. So our next step is to first, of course, demonstrate that Watson has a competitive champion level performance at this task. But of course, beyond that, to continue to demonstrate leadership in the broader scientific community. And of course, to take this technology and demonstrate how it can be used in business application, including healthcare and life sciences, tech support, enterprise knowledge management, government, finance. There's lots and lots of areas where if you can get a better handle on all that rich content, you can make better decisions in your business.
Oh, yeah, I'll run this one.
One of the things I like to talk about a little bit to kind of inspire the imagination here is how this kind of technology can help in medicine. If we think about when a doctor, a physician staff has to come up with a differential diagnosis, what are they really doing? Something very similar to what happens in Watson today and what the deep QA technology enables. It starts with looking at lots of information, whether it be symptoms, family, patient history, medications. We have huge volumes of reference text, journals, abstracts. We have databases and knowledge bases. How do we bring all of that together to produce a differential diagnosis. Well, guess what? A differential diagnosis is a set of hypotheses. You have to combine, look at it, analyze all the evidence in support of the different possible answers or the different possible diagnoses. Ultimately, combine all those confidences to understand which of those diagnoses is the most likely in a particular case. We think that this works not just in healthcare, but also in other areas that we mentioned, like technical support, business intelligence, market intelligence, finance, and so forth.
Okay. So that's Watson, which is, in terms of technology, it's a decade behind, but in terms of demonstrated performance, it's, we still haven't seen anything like it. And they wanted to apply it to healthcare to help people do originally cancer diagnoses, because cancer is not really a disease. It's, one doctor describes it to me as more of a symptom. It's like saying somebody has a fever, right? So it's hundreds or thousands of different diseases underlying. And it didn't work out very well. There's some interesting articles about what happened, but they ran into, so they put $1 billion into creating the Watson division a few years after this video was made. And they ran into problems in the medical side of things like the electronic health records didn't contain the data that they need. It was hard to and expensive to license feeds for the journals that they wanted. The doctors were already quite good at this, and so the computer wasn't really that helpful to them in some contexts. Apparently, in some hospitals in less developed countries where they just didn't have staff who were trained to that level, it was more helpful. It was sort of a way to get a baseline standard of care, but basically failed. And I think the lessons why are very interesting and will tell us something about the limitations of general AI. Nonetheless, I would love to have one of these for journalism. I would love to be able to just have an interface. And I've written about this. I called it Izzy after I.F. Stone, who was an American journalist who did a lot of their work from documents. I'd love to be able to say, you know, Izzy, tell me if there are any records showing payments to a shell company, right? And have learned what a shell company looks like. You saw in that video use of structured methods, you know, those parse trees that we were looking at, and, you know, probabilistic relations. So that extends the triple store model we've been looking at to have a probability on a relation, which starts to move towards more modern methods. So you can imagine the Bayesian graphs being used to do inferences on these things. But I think one of the really interesting things about Watson is it didn't try to turn the world into structured data first. This is from a paper, Furch is the guy you just saw talking. This is from an overview paper they wrote about how they put it together. So it uses a triple store. There's a ton of stuff in that triple store. You can saw they put WordNet in it. They put DBpedia in it. They put, you know, everything that they could get a hold of. But very rarely do they actually look up the answer to a question in a triple store. And that seems to be because to extract relationships from text, you need an ontology. You can't really know what the right ontology is without considering the question. So while we're starting to see graph databases used in journalism, and they seem to be a very convenient representation for structured data. So if you have a lot of different tables and you want to merge them all into one place and do record linkage, it's probably going to work very well. If you want to start with a huge set of documents and pull information out of them, it may actually be better to, I think of it as late binding or lazy evaluation of the information extraction. In other words, to parse the text of the documents at the time you're evaluating the query, as opposed to trying to do it beforehand and then just operating on structured data. Because you know, when you look at this stuff and you have to make decisions about how you encode, those decisions are going to depend what you're looking for. So unless you know exactly the type of questions you're going to ask in advance, probably you need to be thinking about things that look more like search algorithms than knowledge extraction algorithms. That's my theory. This course is called Frontiers of Computational Journalism. We're definitely at frontiers. Nobody's built anything like this. But my guess is that the first successful general question answering algorithms in journalism are going to be based on extracting relationships after the system already knows the question. I want to leave you with a quote from Leibniz, who, you know, co-inventor of calculus. This is a lovely article on the computational imagination. And the "let us calculate" is a quote from Leibniz. Yeah, check this out. The only way to rectify our reasonings is to make them as tangible as those of the mathematicians, so that we can find our error at a glance, and when there are disputes among persons, we can simply say, "Let us calculate," without further ado, to see who is right. So Leibniz, and he wasn't the first and he wasn't the last, hoped that if we could represent all knowledge in the right symbolic form, then we could answer all questions by calculating, that is, by applying formal or mechanical methods. This vision has not come to pass. It was the vision that ended in failure for the first wave of AI research in the 80s. I still don't think we've got it solved, but the reasons why this doesn't work are very deep and complicated. All right.